Welcome back, everyone. So, if you're gearing up for your thermal engineering finals, you are literally in the exact right place. Today's explainer is your ultimate prep guide to mastering one of the, let's be honest, most notoriously tricky topics on the whole syllabus: internal convection. We're not just going to sit here and memorize equations today, right? We're going to actually understand them so you can absolutely crush whatever curveball problem your professor decides to throw at you. All right, let's run through the game plan for today. We've got 5 key stops. First, we'll track the journey of a particle. Then we dive into the thermal entrance region, followed by the fully developed region. After that, we're comparing laminar versus turbulent flow. And finally, we'll lock down those key formulas you absolutely need for your exams. Okay, let's jump right into part 1, the journey of a particle. To really wrap our heads around the heavy math coming up, we're going to ground this whole review by following a single imaginary fluid particle right from the second it enters a pipe. Picture this. Our little particle enters a totally new environment where the pipe wall is at a wildly different temperature than the fluid itself. Boom. As soon as our particle and all its friends hits that wall, a reaction kicks off. The fluid starts heating up or cooling down to match that wall temperature. This interaction drives convective heat transfer, which builds what we call a thermal boundary layer. As the fluid keeps cruising down the tube, that boundary layer gets thicker and thicker, pushing inward, until eventually the whole entire tube feels the effect of that temperature change. Moving on to part 2, the thermal entrance region. Now, taking a look at this diagram, I want you to focus right over on the left side where the fluid first enters. See those pink lines? That's our thermal boundary layer. Notice how the fluid starts to heat up or cool down, and because of that, you can literally see the boundary layer thickening up as it moves along the x-axis, from left to right. Inside that growing pink zone, the fluid's temperature is actively, constantly changing. That whole section right there, where the layer is still expanding and the temperatures are in flux, that is your thermal entrance region. Now listen up, because for the exam, you've got to nail the exact terminology. The specific distance it takes for this boundary layer to develop, like from the very entrance of the pipe to the exact spot where those boundary layers finally meet in the dead center, is officially called the thermal entry length. You're going to see this in your textbook and definitely on your test, written as L sub T. And hey, just a quick side note, while the fluid is actually inside this zone, we call it a thermally developing flow. All right, let's keep moving down the pipe to part 3, the fully developed region. This graph visually maps out the math for us, and honestly, this is the ultimate aha moment for engineering students. Check out the top graph, specifically that upper pink line marked H sub x. That is your local convection heat transfer coefficient. You see how it starts off super high over in the entrance region on the left? That's happening because the thermal boundary layer is still super thin, so heat transfer is incredibly rapid. But, and here's the crucial part, watch what happens as we move further right into the fully developed region. The curve completely flattens out into a horizontal line. So, why should you care about a flat line for your final exam? Well, because a flat line means a constant value. Once we hit the fully developed region, the flow becomes completely steady. The value of our convection coefficient, H sub x, just stays constant. And that is a huge relief, right? It means all those complex, constantly shifting calculations we had to deal with in the entrance region suddenly become totally predictable, constant, and way, way easier to handle mathematically. Actually, if you get hit with a conceptual multiple choice question on the test, I want you to remember this exact textbook quote. Fully developed flow means the temperature gradient no longer changes with distance, period. The temperature pattern is officially locked in. It's just not going to change as the fluid keeps traveling further down the pipe. Which brings us to part 4, laminar versus turbulent flow. Let's break down the difference here because it's huge. In laminar flow, the fluid is gliding along in these nice, smooth, parallel layers. Heat spreads mostly through molecular diffusion, which, let's face it, is pretty sluggish. And because it's so slow, it takes a much longer distance down the pipe for that thermal boundary layer to creep inward and finally fully develop. But throw turbulent flow into the mix, yeah, everything changes. Now you've got random fluctuations, chaos, and intense, rapid mixing. That violent churning completely overpowers the slowpoke molecular diffusion. Because the fluid is mixing so incredibly fast, the temperature equalizes way quicker, which gives us a drastically shorter entry region where the boundary layer just merges almost instantly. And finally, part 5, key formulas for exams, the stuff you really need. Okay, let's walk through sample problem 1. Say you're sitting in the exam, and the question asks you to find the thermal entry length for engine oil flowing smoothly. Smoothly is your keyword for laminar flow. The second you realize it's laminar, you immediately need to hunt down 3 core variables: the Reynolds number, the Prandtl number, and the pipe diameter. Honestly, don't even try to solve the problem until you've got those 3 pieces of the puzzle. Now, you might want to literally take a screenshot of this table right here because it is your ultimate exam cheat sheet. For laminar flow, L sub t is approximately equal to 0.05 times the Reynolds number times the Prandtl number times the diameter. See how heavily it relies on Re and PR? But let's flip to sample problem 2. Imagine water rushing turbulently through a pipe. Because of all that intense mixing we just talked about, the formula simplifies massively. Like L sub t is approximately equal to just 10 times the pipe diameter. That's it. It is completely independent of the Prandtl number, and its connection to the Reynolds number is so weak that we just ignore it for practical calculations. So in almost any real-world tube flow problem, you can safely assume the thermal profile is fully developed after just 10 pipe diameters. To wrap up this explainer, I want to leave you with a thought that kind of bridges the gap between your textbook and actual real-world engineering. If turbulent flow hits a fully developed, highly predictable thermal profile in only 10 pipe diameters, which is insanely shorter than laminar flow, how might a design engineer use that exact rule of thumb to minimize the length and the cost of heating pipes in a totally cramped factory layout? Think about it. Forcing a turbulent flow regime could literally save huge amounts of space and money. Keep that in the back of your mind while you're studying. You're not just trying to pass a test. You are learning the tools to actually build the world. Good luck studying. You're going to do great.